So I'm going to follow on from the previous presentation last week, where I was trying to give a quick introduction to Nova and its architecture, with some tips on how to work upstream and those kind of bits and pieces. And I'm going to try and look at upgrade of Nova as a way in which we can test whether we're actually understanding the architecture of Nova. So let me set some context on upgrade. So what are the needs of upgrade? So first of all, let's define the scope of the upgrade. Now, Nova basically supports two kinds of upgrade. The first one is sort of obvious. You can upgrade to the latest release of Nova from the previous release. We often call this like an n to n+1 upgrade. Now, if you use that n to n+1 terminology, Nova only supports n to n+1. It does not support n to n+2. So you have to roll to each stable branch. Basically, each supported stable branch every 6 months, or at least you need to move to each step. That's the scope of the release to release. The other thing it supports is something that's been called continuous deployment. That's probably a bad way of describing it. But basically, you can keep on the master branch and upgrade between any two commits on the master branch. I say any two commits. It's any two commits within the same series, technically speaking. So stay within the particular series you're in, and you can upgrade between subsequent commits on the master branch. And that's the basic scope of these things. So we also talk about upgrade in two terms, which is this control plane and data plane upgrade. So the data plane, that really means the VM being still alive, or the bare metal machine, so the server still being alive, and that being able to communicate via the network and those other pieces. So is the user's instance within the system still working? So that's the data plane. And the control plane is about the API being up and all the infrastructure to manipulate the data plane. One of the design tenets of Nova when it was first created was that there was always this control plane and data plane independence. You can kill the whole control plane, and the data plane should happily keep going. So the idea is that you can upgrade the control plane by taking down the whole control plane and bringing it back up without affecting the user's instances. This is kind of a fundamental concept since the beginning of Nova, really. Something that's slightly more recent is this idea of when you're doing the upgrade, you shouldn't have to change your configuration file. So when you're using release n+1, you should be able to use the configuration file that works just fine with release n. The idea is that you upgrade without changing the configuration file, then you go through that configuration file and update all the deprecated options, deal with all the name changes that have happened, the deprecated names. So you have a clean configuration file. That means that that clean configuration file should then be able to be used for your next upgrade. So it kind of split. You don't want to have all your upgrade changing while you're trying to do the upgrade. Well, you don't want to have all your configuration changing while you're trying to do the upgrade at the same time. So that's sort of part of the aims there. Following on from that, when you upgrade, you don't want features to magically disappear. So you really want to make sure that before you remove anything, you're warning users about the removal. The removal should be a very exceptional thing. We never really want to remove features. It's just that sometimes features aren't being maintained and are so broken they've got to the point where, hey, we need to replace this. So we need to remove this and just drop it. There are some features that are being replaced. So the deprecation is more about, hey, there's this new way of doing this thing. Please go deploy this new project to have the EC2 API or such like. So there's those two kind of deprecations, a pure drop and a new way of delivering the functionality. And fundamentally, we need to be able to warn users about these coming, which gives the whole community an opportunity to revise that decision if it turns out to be the bad idea. Now, this kind of general pattern about deprecation and the configuration and everything else has been packaged up as a project assertion tag. So there's a link at the bottom here referencing the, I've sort of hacked into the slide, that you can look up and see in the governance repo certain tags you can apply to a project. So Nova has several of these different tags. So there's tags about the deprecation cycles, there's tags about ensuring that you can keep using the existing configuration to have an easy upgrade. Then there's another tag about like rolling upgrades. We'll get onto those later. So what's the old process for upgrade? What does it look like? Basically, it's kind of this simple three-step process. You turn off the control plane. You muck with the database so it's in the new format. That can take quite a while if you've got a big database. Then you turn back on the new control plane, and whoop, everything's working. So that's the kind of idea. And let's remember back to the control plane versus data plane independence. You can basically schedule this maintenance so you don't have API connectivity during this time, but your users' existing instances shouldn't be affected. Sure, they can't delete them or snapshot them during that upgrade process, but they should just keep running and should be unaffected. But yeah, you can't, but you lose the API during that time. Now, the reaction to this was, from our users, was something like, hey, why are you doing this to me? I want to be able to create my instances at any time in the day. You know, with a global cloud across multiple regions, there isn't really a time when people don't want to create. Sure, there's a time when there's less creations than your peak, but there isn't a time when people don't want to create. So we need to avoid like having that total outage, or at least reducing it. So there's two main types of upgrade that I really want to think about here. The first one is the concept of a rolling upgrade, which is basically how can we make the downtime during the upgrade process as minimal as possible while keeping the process relatively simple. But then there's the next step from that, which is like zero downtime upgrades, where you're basically saying, hey, we don't want any downtime of the API during the upgrade. Asterisks against any, there be dragons, but you want the API to be up all the time, pretty much. There might be delayed actions, I guess is what I'm trying to say. So let's look at where Nova is looking at taking its upgrade process. So this is really what we're talking about people doing for the Mataka release. So there's some new features added in Mataka that make this kind of thing possible. So before, you remember there was the turn it off, tweak the DB, turn it back on again. Now the first step was basically, well, why can't we expand the database before we do the turn it off, turn it on, so that you can just do expand database, then turn it off, then turn it on. So you want the database schema to work, the new database schema to be not breaking your old code. So that's the first step in this process change, is before we start, we can expand the database schema. Now the next step was, let's look at how many nodes there are in Nova. There's an awful lot of Nova compute nodes, and there's a small number of other nodes. So in order to reduce that downtime, what we could say is the small control plane nodes and the API nodes, let's restart all those first so that they're all using the new code. So let's turn them all off, turn them all back on again. And then what we do is we make sure that we can have old compute nodes with brand new everything else. This is reducing that downtime, right? So the next piece is we can then slowly, one by one, upgrade each of the compute nodes at a time where they're not going to be affected. So we can ask the compute node to do a graceful shutdown, it shuts down, and then start up the new process. We can do that one by one when it's convenient for each of those compute processes. At the end of all that, we have all the services running the new code, and that's where we basically have to send a SIG-hop signal to all the services, basically so that they can refresh their information about what nodes are running, and they can realize that everyone's running the new code, so that they can then turn on all the protections to make sure that you don't have old nodes coming back up and breaking the system. So anyway, lots of waffling there. So the new process is expand the database schema, restart the API and the control plane, then slowly restart all the compute nodes, and then we need to do something just to let everything know that we're finished, to sort of finish off the process. There are some extra details in there that I'm skipping over, but that's the general scheme of things. Okay, so let's dig in a bit more into how this happens. And I just wanted to refresh the Nova architecture slide from the last session. So this is taken from the developer docs. So let's just remember what happens when an API call comes into the system. The REST API, we call the REST API, end users call the HTTP REST API. That very often gets sent to the conductor after being recorded in the API. The conductor, like for a build request, for example, has to call the scheduler to find out where that happens. It gets a reply from the scheduler, which then tells it which specific compute node to talk to. And that then pulls from all the external services what's happening. And then the API, well, via the database actually, the API is then saying, yeah, we're done. So you can see the control flow here. Now, let's switch over to this other view of the system. So this is the view that I was presenting. This is basically the same view, just not as pretty. So let's have a look at the architecture, but let's drill in to different pieces and how they relate to upgrade. So first of all, let's look at the database. So last time we looked at how we use SQL Alchemy to access the database, and we have SQL Alchemy migrate scripts that do the schema changes. What we didn't look into actually data migrations. So originally, that do the database piece included schema migrations and data migrations. If you imagine you're renaming a column, there's two ways of doing the rename, right? You could just send to the database so say we're renaming a column from, we're converting a column's format and doing a rename at the same time. Say we're changing it from a string to an integer because of various reasons. Let's not go into why. And there's a clear mapping from all the existing strings to integers. Let's just say that's true. One way we do that is in one script we can add the new column, copy all stuff off, do the conversion, and finish. And then say we're done. Now, that means that we can't have anyone else accessing the database during that time, right? Otherwise you start getting updates in the wrong columns and it will get very confusing. So what we've done for migrations is we split the schema change and the data change. So during the new upgrade process, we initially change the schema, so we have the old and the new columns there together. Then inside the code, we actually, inside the Nova objects layer, we do the conversions online. And we make sure that we don't start doing conversions until we know we've got enough of the nodes upgraded so that it's safe to actually do that conversion piece. So that allows us to do these data the database migrations without any downtime. So you do the expand in advance, then you do the migrations. The following release, we can actually do the contract. So the next cycle will remove that column that's no longer used, and we'll only do that if all the data migrations have completed. So it's kind of expand and contract, but it's across the two releases. Something I mentioned very quickly is graceful shutdown. This is sort of a way in which we can get to a graceful upgrade quicker. Currently, when a compute node is processing something, if you do a SIG kill, we actually lose, we can lose data, and it's just not very graceful. The compute nodes are not very good at handling that. There's a lot of logic for when the compute nodes start up to go and try and fix it. So for when there are actual failures, we try and fix it up. But generally, it's just not very good at, it's very messy doing that. So the idea to try and reduce this problem is to have graceful shutdown, which is basically where the compute node says, hey, I'm not going to process my RPC queue anymore, so I'm not going to start any new actions. I'll just finish off what I'm doing and then stop. So that allows the shutdown to not lose any actions. Then you can start it back up with the new code. So that's the graceful shutdown. It does that basically by when you send a SIG term signal, it does particular processing within the service object. Now, when I was describing the upgrade process, I was talking about having all new nodes, a mix of new and old nodes. So if you look at this diagram, the red nodes, all the control nodes at the top, and one of the compute nodes here is all running new code. And then we have these sort of greeny, bluey nodes that are all doing the running the old code. So in order for that to work, what we've actually done is made a hard versioning scheme for the RPC interface between the compute and all of the services. So it's the compute RPC API that's got a strong version on it. What we do is we actually say, let's make sure that we're talking the old version of the code, so the code that the RPC version that the blue nodes, the bluey greeny nodes are running, so that the new nodes support the old scheme. Once we're all running all the new nodes, we can then move to the new version of the RPC interface. This just makes it much simpler for working out what's going on. So basically we pin the RPC version at the old version, so we talk old versions to all the nodes. This is actually quite complicated to do for the operator. To make it easier for the operator, something we added in Mataka is the ability for Nova to actually know what the RPC pin should be. So all the compute nodes are reporting a version that implies a particular RPC pin. So we can find what the minimum version is and apply the appropriate RPC pin without the end user actually having, the end operator having to pick a particular one and put it in the config. That SIG hub I was talking about basically says reload configuration. When you do a reload of configuration, one of the things all these services should now do is drop their cached RPC pin so that the next time you call something, it recalculates the RPC pin and should work out to use all the newer versions. So you can actually refresh the RPC pin that you're using. So that's how you can use the system to help refresh the RPC pin without having to do a restart of the processes. You can just do a SIG hub. Now I said we had a strong version interface on this RPC system. The RPC signature it's really only versioning the signature. So if you've got new, if the semantics of what that method does change, or if the arguments you pass in change, then there's a version bump. But it doesn't control the data that's being passed across. When we first, when folks first built Nova, that was originally passing dictionaries across the wire. What we've moved to doing is passing a serialized version object across the wire. So that when you pass the data in those the data in your arguments. They're actually versioned pieces of information. These versioned objects are actually how we now basically we use as a tier to describe the intended representation of the object rather than its implementation detail. So all the new code is always using the new version of the object, regardless whether it's in a compat, doing compat and stuff. So it's all using the new version of the object and always sending new versions of the object. And the database, depending on how the data migration is going, depending on if you've got some old nodes around, which means you can't do the data migration, the database schema might be completely different to the object itself, but the new code is just working on the new object, and the object layer is dealing with all these differences. That's one part of what objects are doing. The second part is what I was saying is we use them to pass them across the RPC wire, so that if you get a new object sent to one of these old compute nodes, it can actually talk back to the conductor using an API it already understands, saying, hey, give me the old version of this. I'm expecting version 2.9 rather than this one you've sent me. Please give me 2.9. And it inspects the object and works out how to backport that object to the 2.9 version and forwards the 2.9 version to the service so it can continue on with what it's doing. It's not particularly efficient. We might find a way of actually automatically back-leveling the version when we know we need to. But for now, for simplicity, that's how it's working. Yeah, for simplicity. So we've got the objects basically making sure that we version the payload sent across the RPC, and it's also giving us an independence between the implementation in the database backend and what the code is trying to understand. Okay. Has anyone got any questions about that? I've sort of been waffling on about the upgrade for quite a while. Well, let's keep going. So what I want to do is look at how that new upgrade process maps onto this architecture diagram. So the first step is the database expand the schema. The second step is all about ensuring that you're running the new control plane and the new API nodes. And the third step is where we slowly start to upgrade each of the compute nodes using the graceful shutdown procedure. When we've got everything all upgraded, we need to update the RPC pin, and we can do that using a SIG hub signal to all the different services. That's worth noting in this diagram. I've been describing the process for minimal downtime upgrade, right? So there's a time where the API is all turned off. What we want to support to get to zero downtime upgrade is having new and old API nodes sitting behind a load balancer. And the idea is you have the requests coming in and they get routed by the load balancer. New requests get routed to the new nodes. And once all the old API requests are finished, there should then be no connections going to the old nodes, so you can then decommission the old nodes. So you can sort of transition across. But because you've still got those active API requests still going through the old nodes, in Nova it should be pretty quick. But it's very rare that there's an API call that should take longer than a minute. So you've probably got about a minute with this overlap, but you've still got overlap. So in this world, we've got old and new API nodes. Now, the API has direct access to the database, whereas the compute nodes, their database access is all going via the Nova conductor running the new code. So there's a difference here. to keep the compute nodes running for a long time. We have all that object backporting and everything, so all the database traffic gets proxied through the Nova conductor. With the API nodes, we actually have the raw database requests for old and new happening at the same time. Now, the way in which we support this in Metaca is that we actually report the service version for the API nodes so that we can tell when we've got a mix in old and new API nodes within the conductor node. So the conductor node is running the new code, but it understands that there might be old API nodes around as well as old compute nodes around. So it makes sure that there's no data migrations that happen until you have all the things that access the database on the new code. So you don't actually have to wait for all the compute nodes to be upgraded before you do all your data migrations, but you need to make sure that all the API nodes and control planes are upgraded. So that's how we got to the zero downtime rather than just minimal downtime. Basically just by delaying the data migration. Okay, so that's quite compacted kind of overview of upgrade. I guess there's a whole bunch of questions, but let's open the discussion for questions.
Okay, great. Thanks, John. Can you just go over again so the conductor's role is to sort of insulate the database, well, I guess the other way around, to insulate the code from the database. So you can have some older code running, but the database will have been all migrated. So I guess I don't really have a question. I just want to say that again. So the oscillator versioned objects, so the code's going to have to, when it makes a request, how is that working exactly? Does it pass along the object that it has, or what's going on there?
So good questions. Let's talk about the two cases I was talking about, right? So we have the old and the new API nodes both talking to the database. Now in this world, they're not isolated by the conductor. So that means that we have to have logic in all those database calls that are happening to work out if there are any old people about accessing the database. So it does that through the service versioning. So basically it has to hold back the data migrations until you do that. So let's think of an example. So I talked about creating a new column and moving all the data to there into a different format. So going from the string to the integer, say it's an enum, so we're changing the string to the integer. Now, in the data migration we have to do, right? If we start moving that data across, but we have old code updating one column and new code updating the other column, we have a massive problem. So what we've actually done is made sure that whenever those kind of situations happen, we just keep using the old stuff until the point that we know all the new, all the people that access the database can switch over. So that's one technique we're using for the two API databases, basically, two old and new API nodes. Now, this contrasts actually to the slightly older approach we're taking with the compute nodes. Now, it's expected that the compute nodes will be running for a much longer period of time on the old code. So we want to try and get to a steady state with the data migrations and things quicker. So we want to get to a point as soon as possible where we can do all the data migrations and get using the new schema. So you can have all the old compute nodes and a brand new schema. And the way that we support that is by having all database calls that the compute nodes ever make going via the conductor. Now when you look at the code itself, how this actually happens is you'll see the compute node will just do instance.save. And it will do instance.get by UUID and such like. Now all of these calls, if you look at the object code, have got the decorator @remotable. And what's happening there is whenever you call one of those in the compute node, the compute manager's initial startup code actually registers with the object system and says, hey, whenever you make a remotable, please call the conductor to do that code. Now, all the API nodes, they don't have that initialization done, so any of their object calls happen in line, so you run the actual object code in line. Basically, you have to do that on the API for efficiency. If you're going across the RPC bus for all the API calls, it would really suck. But yeah, so you've got the compute nodes. Basically, when they call an object function, the remotable decorator means it's calling the conductor. And what it basically is like any other RPC call. There's basically one master RPC call where it says run object method. So you've got the object class, its method, and then all the arguments that were passed to it. So they get sent across the RPC bus and executed on the conductor and sent back. The sort of interesting thing to note is that that one RPC call can be within a single database transaction. So it's up to the conductor how that gets implemented. But of course, you can't have a database transaction that spans multiple RPC calls. It just doesn't really work like that. Does that give more context?
Yeah, thanks.
So zero downtime testing is kind of tricky. Are y'all actually trying to do anything upstream? A grenade test wouldn't be enough, right, for zero downtime. You'd have to test between each and every commit on master.
Yeah. We haven't got any way of testing zero downtime yet, which is why we're not claiming it for the Mataka release. It's sort of an experimental feature. People claim it works because we've sort of vaguely tested it one-off. But you're right. What gets tested upstream is the multi-node grenade. A multi-node grenade is basically testing the minimal downtime case. So it's testing, have the old system running, so it installs the previous stable branch. Actually, pinning the dependencies in the stable branch become important because of multi-node grenade, of course. So yeah, you're running all the old stable branch code. Then you go through the process. So you do the database, expand, then you turn off all the control plane and for the old code and put it on the new code. So this is where you've got you've got one old compute, one new compute, and a new everything else control plane. This is grenade multi-node, right? And so we can do things like there was an experimental test done to say, hey, boot an instance and live migrate it twice so that you can prove you're going both ways between the compute nodes. So you can do that level of testing. But yeah, that's only testing that kind of minimal downtime case.
Will that be discussed at the summit, perhaps? How to test the zero downtime stuff?
Possibly. It depends whether we still want to invest the time and effort to actually support that. Like minimal downtime might be enough. And the only reason I'm saying that is because right now, right, every single Nova commit has to be reviewed with this whole upgrade picture in mind before approving it. Now, some changes clearly have they're not affecting upgrade, but you have to sort of know this process intimately to actually work that out. So that the minimal downtime is easier to reason about than the zero downtime. I'd say that's not decided yet.
Gotcha.
It might, so that the case that I would like us to support is probably a slightly more complicated case for the multi-node grenade, which is where you have old and new API nodes alongside new control plane and old and new compute nodes. I think if we could test that case, I'd be interested in the testing. If you didn't, you know what I mean? I think I would get is like it doesn't mean it's like you can technically do a rolling upgrade of all the compute nodes, all the conductor nodes, for example. So you can have old and new conductor nodes, but testing that seems like an absolute pain. Yeah, I think you could do a Tempest run on the old and the new API side. It's just that at this point, the test is taking too long for the Jenkins, for the test run. It's already the long poll. We make that poll longer. It's a bit scary.
Gotcha.
So, John, I have a question. This is what you explained is a happy path. What happens if there is like one, you're already like halfway through and one compute node, it throws some error. So how do, and also as an admin or something, I do need like some ability to abort my upgrades or rollback or something like that.
So we don't actually technically support rollback.
When I say rollback, I'm more into like where we are halfway through the upgrades and then upgrade error happen, and then what do I do with the, like half nodes are new code, half nodes are running the old code.
So the official plan right now is you fix the bug.
Okay.
Which I agree is not a proper answer. So I honestly think rather than focusing on the zero time case, we should actually focus more on the rollback case of the minimal. Right now it's not in any way tested. So let me talk about that for 30 seconds or so. If you consider, so basically the thing that we can't do if you want rollback in this system is the data migration piece. So right now what we're doing is we're saying, hey, let's not do data migrations until we've upgraded all the new and old API nodes. Now we could actually make that a bit more manual. To basically say, let's get to the point where we're running all new code on the old schema, and only then start doing any data migrations. So you can actually do this today. It's just you'd have to keep running a dummy old API node to actually stop it doing any data migrations, which is pretty dumb, right? But I think you can actually just roll back to the old code at any point if you haven't started doing those data migrations. But that would require another Grenade multi-node job to test it, right? Because technically we'd have to run Grenade multi-node to make sure that the mixed case works. Then we'd have to turn it all off, put all the old code back on again, and then run Tempest again to validate that we're able to then, correctly pass Tempest, having done the rollback. We don't test that today.
Okay. And this is Nova upgrades we are talking about. My question might not be in this context, but how about if I have some patch which is related to some bug of hypervisor running underneath Nova?
Do you mean, hey, so when I said that there's data plane and control plane independence, what this whole process is assuming is that you don't upgrade your hypervisor, which is an intriguing assumption, right? Now, what this is really doing is just splitting the problem in two. So there is a whole different problem, which is, hey, I need to upgrade my hypervisor. How do I do that? Now, there's some really cool things that the hypervisor community is working on around live patching, so that you can try and actually move forward, so live patching of QEMU and live patching of the kernel and live patching of the Zen hypervisor itself and all these kind of things. Basically, for the use case of, hey, there's a security bug, let's move on. Now, when you look at what some of the distros are doing, like I believe the Red Hat distro does some of this. You can actually consider the compute node upgrade as in a different way. So let's talk about running old and new compute nodes. If you can add a little bit of extra capacity, or you have some spare capacity, you can live migrate all your instances on your old compute node to a newer compute node, and then you can kill your old compute node and make it a new compute node and a repeat. So that's one technique that's being used to basically upgrade the hypervisor itself in a rolling fashion with minimal impact to users. Does that make sense?
Yeah, yeah.
Actually, there is an extra requirement that's hidden in there, is that we need to be able to support that live migrate between old and new compute nodes, which is currently not tested in the gate.
Makes sense. Okay. Thank you.
We've done some manual testing. Well, the reason it's not tested in the gate is because the current versions of libvirt in the gate, I believe, cause a failure rate that's too high for us to actually make that test voting. It's not that you can't test it.
So when you talked about that Jenkins is the long pole for testing, is that means all these test cases has to go through Jenkins? Can't we just have a Nova Jenkins instance where it just do the Nova testing and all? Why it all has to
I was being very, very inaccurate. So I don't really mean Jenkins. I mean the run of the job. So Joule is a magical beast. It's basically. I don't know if you know how the node pool and Joule thing actually works. But basically, node pool is responsible for making sure that there are nodes of a particular type available across multiple OpenStack clouds at any point in time. So it has settings like make sure they've always got 4 of these nodes available. I think infra it's a massive number, right?
Okay.
Sure, there's always 100 ready. And what it does is whenever your patch comes in, it grabs n nodes, where n's the number of test runs you need for that particular job combination, and it starts them all off in parallel. And it only votes back with a +1, -1 vote, which I think is called the Jenkins vote. So it +1, -1 is just the aggregate, the union result, basically from the test run. So if there's any failure, you get a -1 from Jenkins, but really it's Joule doing all this magic. So what I'm really meaning is when you look at the Grenade multinode, it's basically one of the jobs that's taking the longest amount of time. So if that takes any bit longer of time, then it means that our overall voting back from the system takes longer.
Got it. Okay.
Hi, John. I have a question. So,
Sure.
in the migration process, do we acquire lock on database?
No. Now, I say that in a flippant way. What we do is we do all of the moves within a database transaction, and as you would with any other database call. So it's basically, that means it's taking out a row lock on the update that you're doing. But it's that's just basically using the ACID qualities of the database that you've got underneath.
So that just means it can take a long time depending on how much data you have in your database.
Yeah, there is actually a Nova manage command to run through the to preemptively run through all the objects in the system that potentially could require a migration. So you don't actually have to wait for your system to touch every object within the system, if that makes sense.
Yep.
It has that Nova manage command basically has a don't do any more than n updates, so that you can run that in a loop and make sure that you don't upset your database. So I know in our public cloud production, for some of the database pruning activities, what we actually do is that we monitor the lag on our read slave databases. Because if we do too many transactions on the master databases, the read slaves get too far behind. But the tooling is all there to allow you to throttle that.
Yeah.
It's always tricky.
It is. Cool. Yeah, with a lot of this stuff, the devil's in the details, honestly. It's when you dig deep and look at what you have to consider in your head at the point in time that you're reviewing and or writing the code that's trying to worry about these migrations between it. I don't think we've got a single data migration that was bug-free on the first commit, despite it being written by the people who've built this whole framework, both of them.
Okay, well, it sounds like we're going to wrap it up exactly on time. So thank you, John. I guess go ahead and hit stop and